Back, everyone. So we're going to start this session with me speaking for a few minutes, carrying on the answer to the question that Ben asked earlier. What do we know about other forms of queuing system that might be useful and transform to this? And that will be an introduction to Xiao Zhang's. Going to spend 5 or 7 minutes just with some slides about time constants. So let me just speak for a few minutes. This is a model that was developed over the last sort of 15 or so years in studying communication networks, and it's quite useful. You imagine you have a server. It can serve one packet per small unit of time. It has a fixed size buffer, and it has things arriving in the buffer. It gets rid of one per unit time. It has them arriving in some random process. What is the random process of them arriving? Well, one very useful regime is where you imagine that over time, the number of packets arriving a small unit of time in a stream from, for example, a video film that you're watching online at home or something, it has some stochastic structure, and there may be many of these things. Might be the Wizard of Oz. And this might be Die Hard. And so they've got different statistical characteristics, and there's lots of them. That's what the purpose of a router. So this is the output port in a router, and the purpose of a router is to bring things from various places in and send them out to various places. So there's lots of superposition of these things. Now the natural model in telecoms is that these streams are independent. So we're treating, and in that case, the natural limit results from probability theory tell you what will happen if you superimpose lots of these streams and put it through something like this. And what they tell you is what happens when the capacity here, the rate at which it serves, and the buffer gets large, and when the number of these gets large. And they essentially tell you something like the following, that provided the average arrival rate there is less than the capacity there, then what will happen over time is that the buffer size, the buffer length, how high the queue is in the buffer, will behave, that's less than that, so it's sort of bouncing down on zero. But every now and again, it will exceed this high level, which causes you pain. The pain it causes you is that packets are lost, and the quality of service of the people watching the video or whatever is degraded. And it tells you that when this does overflow, it overflows with a particular form of path, a deterministic path you can calculate that depends on the statistical characteristics here. And the models tell you the probability of that for given values of this, this, and this. So that allows you to dimension things. It allows you, for example, to decide how many, you could, for example, run admission control. If a new connection attempts to start, do I let it start, or do I force it to use a degraded coding scheme that uses less bandwidth, or that sort of thing? It allows that sort of decision. So what the maths does is it relates the probability of something going wrong to the other parameters in the system. Now you can see what's different about this. There's several things different. One is that there's just one thing that goes wrong here in overflowing. It bouncing around on zero doesn't matter too much. Another feature is that the mathematics is very much driven by the independence of these streams. That's what lets you get things out. But nonetheless, this theory gave very interesting results about space and time scales. Space and time scales that allowed you to describe statistically very complicated streams here with long-range correlations, with all sorts of things, was one of the attractions of this theory. Independence from source to source lets you have very complicated models over what happened along an individual source. And so that was the prompt for some of us that are working in this area to think, well, that kind of relationship is something that's clearly of interest for things like wind power. You've got a statistical structure that's quite important. You could describe the statistical structure of wind power in terms of, as a statistical object, what its correlation structure is, this, that, and the other. But what we know from the queuing analogy is that the very detailed descriptions of this collapse down to a certain deterministic transform as far as this problem is concerned. And so there is a particular space scale and time scale that, for a particular buffer, is relevant. And so you don't need to, I mean, you could describe the entire, this is, in statistical terms, it's like a sufficient statistic that is what you need to know about this complicated process. A sufficient statistic of low dimension that tells you its performance for a buffer. So the hope is, not realized yet, but not completely out of ambition, that something similar could be found for things like wind power. So that's an introduction here to Xiao Zhang, who's going to speak with some slides on this point. Okay.
Thank you so much. I don't want to make this as another talk, just to try to set a stage for some discussion. So I will not take more than 5 minutes, but I will try at least to do this. As you can see, this is basically a response to very much our first day's discussion about wind forecasting. And wind forecasting, actually most of the discussion is really not about the concrete method to discuss to forecast wind, but actually about how to assess the forecast performance. So to me, just assigning any particular number to the performance, you already lost a lot of information. Also, in the power industry, there's one hidden notion, which is what is the capacity? This fundamental concept all itself is subject to a lot of qualitative or quantitative ambiguity. So, to me, one of the biggest problem is that you want to give a number to the very complicated matter all by itself. We already lost a lot just by thinking this way. So, well, I try to save 1,000 words from here. So when we try to do the window forecasting, what's the purpose? So here is something we're doing the real data with the. Yeah, this is from real data from PJM. And what actually we can do is that we can, for the forecast 3 hours, within 3 hour period ahead of time, we could consistently beating the persistent model. Certainly, persistent model is well known, very difficult to beat just for the short period of time. But well, as this is part of our own work, so we say, so what? So you build the persistent model. The question we receive when we visit in this industry, the system operators, in particular ERCOT in Texas, as we learned from yesterday, this is more or less like an island. You have a lot of wind there. So really, ramping is a huge issue. So they care about the ramping forecast more than the power forecast. So they have some ramping forecast, and the question here is, how can we use it? The same question raised in industry and academia. And so we look at it in a little bit further details about what is the forecast performance. At the ground level, we see, it matches pretty well. And now if you look at the time scale, so you see a gap, they're calling like phase shift, it's a 1 hour shift. And the very dark gray curve is actually persistent model. Persistent model basically means I'm using exactly the value from the previous hour. So what you can see, the difference, this is almost identical to the persistent model, but certainly the good thing when we look at it is that more or less it's to the closer side of the original. But if you look at it from the ramping point of view, the forecasting result is really not that great. But that's really, to me, is not. I don't think that there's any method that can do a good job for this context. Also, another thing we kind of confirm what David said is that they have also the commercial forecast model all the way up to 2 days or 2 weeks probably, and below 6 hour or below 4 hour, our model can do better, but above 4 hour, it becomes messy and it's certainly getting worse and worse compared to the weather-based forecasting model. So which basically means we could use more information for the long-term forecast. So now the question here is that really we need to have a way to evaluate the performance beyond just a single number. So one thing we could do is have this so-called envelope-based. And actually, I was looking for Dr. Labudek, and I don't see him today. Essentially, the fundamental mathematical tools is really the so-called network calculus. And in another word about it is deterministic queuing theory. It's almost like what the way we were doing is a footnote of this. Is the fundamental mechanism or something has been showed up yesterday. You have a leaky bucket. You have something flows in, could be the wind power fluctuating, and then you say you have a constant output rate, and whatever variability is captured in this so-called leaky bucket. So certainly one thing you could do is that if you choose a different level of lambda, then you basically can have this trade-off. Essentially, you have this trade-off between the rate and then the content. If you think about this is power and this is energy, essentially the storage to me is a capacity device because it actually consumes net energy because you have the efficiency loss. But the purpose is that I want to take care of the capacity issue by shifting the load to the energy from time to time. In that sense, it's just like a virtual transmission line, but in the time domain instead of a physical domain. So that's why I echo a lot the Frank's drawing in the previous part. So, and also, this picture you say, oh, this has to do with energy and also power, but the same picture can be drawn in terms of not energy and power. I can actually do this. You have the ramping, power, and energy. They each have the unit megawatt, hour, megawatt, and this is megawatt divided by hour or divided by second, doesn't matter. So really the shift is the trade-off between the power and the energy can be captured by the leaky bucket. In the same way, the energy, the ramping capacity, capability, and the power, the trade-off can be also captured by the leaky bucket. Essentially, it is the variability between these two domains that actually need to be captured by that. So this is the picture reflecting the connection between ramping and the power. You can see the overestimate from our wind forecast can be 1,200 megawatt and per hour, and then but accumulated the maximum error in terms of overestimate in power is like this much, and so this is underestimate. So we can plot this, and if we see the picture, the overestimate side, all the models performs almost identical, but actually, if we look at this, the underestimation side, they could have some difference. So we can have a more refined evaluation of the forecasting error. And the good thing is that this picture can be directly translated in terms of the resource you needed. For example, the horizontal one is how much ramping up and ramping down rate will be needed, and the vertical one essentially is how much capacity will be needed. Certainly, once you have the control designed accordingly, you will be able to accommodate the variability in this domain. So I'm not going through this, but I do want to show you this picture. And basically, this is the trade-off between energy and the power domain. What you can see, this is from California. It's a load. The solid line is about the load, and the dotted line is the load minus wind. It's the net load. So the right-hand side, basically the horizontal one, this is the peak load. And then the lower one is actually the base load, the lowest instantaneous power. Usually happens at night. So what you don't want is, you can see the wind shifted the whole, the spike to the left, which basically means we save some energy. Wind provides some energy. On the right-hand side tell you reduce the peak by a certain amount. However, the negative thing impacted to the wind is that at night, you eat through this base load. At night, you really don't want to have the very low demand there, because that's time very often you have the negative price. You have a nuclear plant running, you don't really want it. It's really very fixed. So you don't want to mess up with that part. So the most important thing is this red line. You see the slope is in terms of the unit is hour. Basically, I can shrink the whole capacity, kind of smooth the power by a significant amount, as long as I can have the storage, in a sense, ideal storage, have the size of 8 hours ratio between the energy content and the power, the capacity. And also, if you look at the tail side is actually not 8 hours, it's 2 hours. In a sense, if you want to build a kind of system, the utility size storage, really the size of the storage should 2, 3, maximum 4 hours would be adequate. When we visit one utility company, they are trying to study the value of the pumped storage project, try to put a dollar value to that. I don't know how to do that yet, but certainly I will learn a lot from our previous talk about try to put the value. However, one thing, specific information I hear, I immediately can respond is they want to do 16 hours in terms of the ratio between the energy and the capacity. Immediately from this picture, we can respond, no, we only need to have like 4 or 5 hours. 16 hours is way too much. So you can use your money in a much better way to adjust the ratio. So essentially, this is what I want to talk about. Thank you so much.
Any questions? Michelle, before?
Let me stay in my... Okay. It's not a talk.
Okay, right. So,
just to clarify that issue of value, I mean, it's the thing I was talking about, in my talk, is that it's infinite if you don't have the resources, and it's zero. And the marginal value of reliability is zero. Once you get some reliability, a little extra, you don't care. And so you have to think, what's the cost of reliability? And it can be, zero or very expensive depending on the resources available. So that's why it's so hard. That was the reason for my joke at the beginning of my talk, is that you can't say. It all depends on what resources are available.
But I suppose the value you're talking about here is shifting of load from one time to another. I mean, it has the reliability. It has all sorts. The storage will have all sorts of other benefits.
Well, the value is infinite. If you don't, I mean, you have to do it in order to run the grid, right?
Right.
And so the value is infinite in terms of the entire economy collapses if you don't. if you're relying on wind power, to feed. But if you think about once you have the resources available, you've done it, and I mean, it depends on what you're talking about.
But it's another way.
The consumer, the supplier's point of view, of course, you want that energy, you're going to have load shifting.
The value today is what would we have to do to ensure reliability now,
Right.
which we wouldn't have to do if we had this. Right.
That's
So,
right.
so, and of course, that means that you're absolutely right. It depends entirely on what you've got available.
So from another point of view, storage really is not an energy device. So in a sense, you need to extract its value from its flexibility, from its capacity. So arbitrage may only get part of its value. So that's another qualitative thinking.
Right.
Just one more comment. I'm thinking a lot about that comment about storage being something like virtual transmission. I mean, you pointed that out. And some places maybe it is, and other places not. So in the Midwest, I think it's not, because in Minnesota, you've always got too much energy from wind. And then on the other side of the transmission constraint, there's never enough energy from wind. So you could have infinite storage, and it would just go and go and go and go, and you'd have to take it by truckload across the transmission line. So that lack of ability to get power from Minnesota to Illinois.
That's not fair, surely, because that's like saying if I build half a line,
Yeah.
building lines is no good because the line goes nowhere. But if I build the second half of the line and it connects two places, then it's got great value.
Well, no, that's
The
not-
the problem is that the storage, if it's part of the network, has to be thought of as part of the network, not a separate thing. So if you've got your storage and you put in some extra lines attached to that, then it does have value.
No, I just meant it doesn't replace the lines. That's all I said.
So is the connection between Minnesota and Illinois, the transmission constraint is full 24 hours a day? Or
I mean, basically, if you could take a look at the website, you've got this incredible difference in prices, almost 24 hours a day.
I see, so it's just
and
full
much
of-
more energy here than there, and so you have to get it across somehow.
Right.
And so and so if you had infinite storage, it'd be like a bucket would grow and grow and grow because there's
Yeah.
much less demand. and the
Yeah,
amount
yeah,
of energy
but I still think the analogy of the sort of space-time diagram of constraints, because in a network there may well be constraints which aren't there, and then constraints which are there, depending upon just that sort of feature.
Yeah.
It's just it's the nature of the numbers that attach to it.
If you built your storage in the Midwest there, we just refer to that as a stranded asset. It would be useless.
Say that again. Wait.
Stranded
It would just be a
asset.
stranded asset.
If what? If
A stranded asset is an asset
No, I
you put
didn't-
in. Yeah.
what was the? You said if you did put in storage without transmission.
Yeah.
Yes, absolutely. That was my point, actually. You have to have transmission.
Yeah. Right. So I suppose the interesting thing about Chow's work and of some of the things that Stan and James have been doing is that you can see these sorts of time constants. You get some value over minutes, over hours. There's particular knees when it corresponds to, say, a daily cycle or a yearly cycle for some of the things. But I mean, I don't know. The various things I've said back up what our speaker there said earlier on, that if you were thinking about building new, you probably wouldn't. It's incredibly valuable, the first one, but the second one doesn't have those ancillary benefits, and it's.
I'm not at all convinced that anybody in their right minds in the market economy would ever build a Norway. You wouldn't even have built the first one.
Yeah, but you do need it for other services.
It would be just much more expensive,
Yeah.
but that doesn't mean there's a market justification for building it.
No, but having built it, there might well be a. Is it used at the moment for any arbitrage, or is it just used for its other services?
It's privately owned, I'm sure it's used for.
Okay, of course. So they've got quite a strong incentive to use it. Right. Okay. Open for discussion on any of the items concerned with today's talks or wider.
Well, we still seem to be struggling to place the storage somehow within a context of transmission or a context of generation. And I was wondering why. The problem here seems to be that we've got all this variability, especially from wind coming into our system. Wouldn't the obvious solution be to place the storage right beside the wind to smooth out whatever is being being supplied into the grid at this point. And in a context like that, I don't really know what is storage in that context. Is it transmission or is it
Transmission.
generation?
Instead of transmission from place A to place B, it's transmission from time t0 to time t1.
Yeah, transmission from time to time.
Yeah, I think one of the reasons we're sort of struggling to place it is that storage in power systems is just a pretty complex beast that does a great many different things. And I guess it's certainly one thing that's been found in studies at distribution level is that in order to get close to storage paying for itself, you have to account for all of these different services that it can provide.
Reliability and
Yeah, reliability, voltage support, you name it. Arbitrage with transmission.
Can I just try? This is a simple model. So imagine just, if there were 3 locations in the U.S. that were completely connected perfectly, never had transmission constraints, and so basically it's a 3-node system, all right? And so Midwest is a bit like that, and then. So then I would, from a control point of view, I think it was sort of like a 3-dimensional system that I'd like to regulate. So I'd like to be able to make the supply equals demand, and there's a disturbance rejection problem. And then each of these storage units is one of my resources. Like an actuator. I was joking about ailerons. I mean, it seems to me that works perfectly. That basically gives me my lower frequency actuation to reject low frequency disturbances. The capacitor banks reject the higher frequency disturbances, and the number of nodes. If I could create a network model, the nodes would depend on where the likely transmission constraints are, and then I get a 3 or 5 dimensional. There's a coarse description. Of course, there's a finer hierarchical description, but this course is level. I've got these resources, which are capacitor banks, storage, HVAC, maybe a pool pumps, and then the transmission constraints just give me the dimension of the problem, and the resources. I don't know. I mean, I think that they're the actuators in the system, and they're very separate from the transmission constraints. I think that's clear. I don't know, but. Because they're what's used to filter out the disturbances, which are locational, and the disturbances rejection is locational because of those transmission constraints. The fact that you can't get the power across means you're going to have separate disturbance rejection in Minnesota, which is very different than disturbance rejection in Illinois, precisely because of those binding constraints.
But one way, just thinking of the previous comment and that comment, if you imagined a network with the transmission constraints in place and the various wind generators in different places, then an interesting question would be where would you locate the storage? Because it might well be that you don't locate it next to the wind power. You don't locate it next to the wind power generator. You may want to locate it a little way in. Imagine a tree structure with wind generators at the leaves of the tree. It may well be that you aggregate the wind prior to it. They may have transmission constraints before they get to the storage, but there's a balance to be done because you probably need less storage if you aggregate. So there's a sort of statistical question there and a network question to try and balance them. Even if you just said, right, all we're going to use it for is for smoothing the output of the wind farm, right? Then where do you put it?
I think the biggest question today is where is it cheapest. So the reason it's not done as you propose today is that the cheapest storage, say in the western United States, is water pumping, for example, or contracts with manufacturing or something like that. Batteries are the worst today. Maybe in the future will be cheaper. We're a responsive gas turbine generators who can do ramping up and down. So the cheapest regulating resources today, you couldn't stick them next to a wind farm. They're big, huge machines or water pumping or something like that. In the future, maybe batteries will become cheaper.
I wonder if you could choose where you place your storage. Would there be any cases other than the tree example where we would actually want the storage to be further away from the source of disturbance. Because I mean, we've got the source of disturbance, and then we've got some disturbance until we smooth it out, basically. And so anything in that part of the network would, well, be subject to disturbance.
I guess it looks as if you. I mean, that kind of description looks as if you're going to put the storage just close to your transmission constraint, rather than just close to your source of disturbance.
Yeah.
Yeah, that's the sort
They
of.
might be next to each other, of course, the transmission constraint and the source of disturbance. But
Yeah, because there's been talk. I don't know where Scottish and Southern have got to with the idea of building further pumped storage in Scotland for that very reason. They were talking about it at one point, but I think that's essentially what the idea you're saying. You sort of put the storage. Put the storage where the constraint is, so you get the kind of free statistical aggregation before you start.
We place it in time and
storage
yeah,
to do further
yeah.
smoothing.
What you're trying to do is sort of route the power over the same physical transmission constraint at different times. So yeah. Chow and then yes, you Chow first. And then.
So one specific consequence of this space-time picture is that really the disturbance has to do with when and where. So that's why, I mean, the coordination in that time and space domain become very essential. So all things that the picture did.
Yeah, I was thinking like, yeah, that's true if there's a transmission constraint, but if there's basically just not enough load to absorb the wind energy, actually it could be good to have the storage quite close to the load, because some of the wind energy that would just be wasted otherwise is absorbed in the losses. So I don't know how much that actually turns out to be, but this is something.
Is there not really playing storage against each other? In some sense, you might be looking at stores in both locations, really, on both sides, so that if there's excess wind and I can't get it through the transmission link at this point in time, and I store it on one side of the link, and then when I can get it through is when I don't have load necessarily on the other side. So then I might be having to look at it on the other side. So there is an interesting interplay. In some sense, what we've talked about a lot so far is aggregate storage and small number of links. But there is definitely an interplay between multiple stores and how you would think about multiple stores in a network and how they would run.
Just, I think if you look at this sort of from a system perspective, all system perspective, I think it makes sense to take this time as your first as your organizing principle, right? So you really the short term is the most valuable, because if you don't run the system right, it's going to crash and you have blackout. And as you get further out, you get more and more resources at your disposal, and value is going down. And even I think for transmission constraints, they might currently not perhaps the case, but they might have something like that too. You could overload your line for a 15-minute service, right? So if you sort of, I'm not sure if you would agree, but you could, in emergency cases, you could make, on the shorter time scales, you have more flexibility that you can use and more incentive to do so. And then the good thing about a lot of storage is that it gives you lots of flexibility in the short term, but you'd have to offset that against impacts later on.
I feel like because we're looking at using storage for two different things here now. One is smoothing out the short peaks, that is a short-term usage, and the other one is actual time shifting of supply. That it seems very much that depending on what we use storage for, there would probably be different locations in the grid that would be more appropriate for it or not.
I think another point leading on from that is we need to consider, and this is when we start moving away from the world of simple models. When we do need to consider the extent to which using storage for one purpose degrades the ability to use it for another. So, for instance, you can generally assume that storage's ability to mitigate some really extreme events wouldn't prevent you from doing certain other things, because almost all of the time you're not needing it for those extreme events. But certainly the keeping something in storage for use for mitigating very short-term fluctuations versus the daily peak lopping to reduce the peak load on generator. That is an example where the two.
So you drag as much as you can by arbitrage. You fill it up, then that prevents you taking spilled power. Or
Yeah. I mean, if you fill it up, then you lose the capability of filling it up further.
But although that does look like it's treatable by a reasonable kind of mathematical model, to trade those off. I think for a policy that manages to not use all your reserve. I mean, okay, you'd need to calibrate the model, you'd need to get the parameters reasonably right, but it does look like it would be possible to get the right trade-off between those various things.
Yeah, I mean, another just in that vein, when are there any mathematical complications associated? This is just something that popped into my head, but so maybe a dumb question. But are there any mathematical complications inherent in valuing storage when there are just other people supplying the same service? So, for instance, if you're looking at what storage can do to help with very short-term noise in the generation demand balance. There was quite a technically very nice paper from Peter Duck and co at Manchester, looking at sort of what storage does in isolation. One interesting question is how the extent to which you can use those techniques to value storage when you've got conventional generation able to do that also.
Yes, so when the service could be provided by another thing. I didn't think there's any particular mathematical complication other than the potential game theory of competition if there's a market clearing, because then the strategies may depend on quite how that market's set up.
Yeah. Actually, I was going to say that it sort of distorts the conversation a bit to say storage, because basically, coal generators today act like storage. The wind goes down, the coal generator goes up, and plays the same role as storage. So it's just talking about any flexible resource, and it could be storage, or it could be generation. And, I mean, right now, people's power systems need scream that storage is too expensive, so let's give up. And of course, there are all sorts of things that are storage like.
So that was the point made earlier about the relative costs of things, and an interconnect for the UK is one that's competitive. Interconnect with other systems.
Yeah, I wonder, I'm not sure actually, would there be any concern for loss or efficiency in terms of bigger or smaller storage? That means one would give the better efficiency. I mean, anybody can, if it is smaller, then would it be less efficient? If it's bigger, is there an optimization thing there?
Well, no, I'm just looking, is there different sizes of storage? Is there, different technologies will have different efficiency.
For example, I mean, I was told that actually by a person from EPFL who was giving a talk, he mentioned there is a paper from IBM India. They actually, in fact, evaluated that smaller storage we use in household, etc., that is 50% efficient only. So it consumes more energy and causes more shortage of supply.
Yeah, 75% was the figure we had for North at some point. But I don't know what was the efficiency of the batteries.
The batteries, I think, are 90% efficient, and they're quite. It's either 80 or 90, and this is the problem. You do it off the top of my head, because that's quite a difference, isn't it? In terms of unit size, I'm trying to think what would affect them scalability-wise. So they come essentially, they're just sort of row upon row of batteries stored up in a container lorry. So they're quite mobile. This is one of the other advantages that we haven't really talked about today, is the fact that something like battery storage, because they come in these shipping containers, you can move them around to deal with particular local network constraints, transmission constraints. So the typical storage scheme, if you've got, say, 20 of these container arrays, that gives you 20 megawatts of batteries. The more you scale them up, I'm trying to think what losses would actually increase. I don't think, I mean, you've got the sort of power electronics conversion, but I can't see that getting worse the larger you get. It's more an issue of cost, because the batteries are really geared towards the shorter timescales for dealing with those kind of challenges. The cost of having more of them is more that the megawatt hours for batteries are very expensive, more than the actual number of megawatts. So for power applications, they're good. For energy applications, there's a limit, there's some threshold beyond which other storage technologies, the kind of pumped hydro schemes, are going to be more effective for dealing with.
Okay, I think we're probably getting close to the end of this discussion, unless there are any other items or topics that people want to bring up. I think we could perhaps stop here and thank our various speakers this afternoon, which I think was, well, yes, we had some speakers. Oh, Chris, go ahead.
Yeah, there was one other point which I think we've touched on a little bit, which is whether there are any particular methods we might use for analysing storage's contribution to mitigating extreme events. I think there are two phases, two parts of that. One is simply how, for this purpose, we would go about characterising extreme events. So we might either have the simple extremes of net demand, or we might have extremes, extreme ramping events, one can look at either of these by simply doing a giant system simulation involving a sort of full time series. But one question is for purposes of looking at storage's contribution, are there any ways in which we can characterise the extremes of either absolute demand or ramping events in a way that will help us gain some sort of insights beyond what we can get from simulation.
So one of the insights from the sort of mathematics of the systems I was describing earlier, or of large deviations in general, is that quite often when extreme events happen that are a consequence of several things, sums of random variables or mismatch between wind power and demand or something, that it's not because any one of them is very extreme. It's because you happen to get the bad luck circumstance that they're all slightly extreme. That there's no individual one that's extreme. The extreme event is caused by the superposition of fluctuations all in the same direction. So that's the sort of thing which would not be particularly picked up by, say, meteorologists, or would be particularly picked up by power systems engineers, but would require the two of them to work out what circumstances might cause them. If they're independent, that would make it easier.
Yeah, I mean, well, we see that a good example of that is the kind of capacity value calculations that Stan and I have been involved in. Is there basically the reason why capacity value of wind can be some way above the credible minimum wind output is that even if you have low wind, you also need high demand and bad luck with conventional generation for there to be a problem. And so I think an interesting problem is whether we can come up with this appropriate characterisation of the extremes, and then whether there's some form of there's some sort of analytical structure where we can value storage's contribution in a way that will give us bit more insight than the traditional giant simulations.
Yeah, I'd like to use this picture there to somehow to respond to, it's not an answer, but just our view of your question. Is that if you look at this horizontal one, this is like a 45 gigawatt, which is the peak load from California area. And what you see is that with the slope, it's about 2 hours, based on this net envelope thing. Basically goes through the lake bucket. Eventually, it basically says if I have storage that can run 2 hours at your maximal capacity, I can basically cut down the peak, the spike of the power by that amount. So basically 2 hours storage size would be adequate. So you can all the way cut your power from 45 gig to 35 gig. So that's basically, in a sense, saying if we manage the storage perfectly, we can absorb like 10 gigawatt the spike.
Yeah.
We don't know when it happens. I don't care, but as long as I get myself prepared.
Yeah. Yeah. I think where the sort of storage aspect, where bringing storage into this becomes particularly interesting. Like it's not a very deep statement, but it's when you start having when you start having either time or energy limits that bite, or other issues where I think there is still it's still a still a fairly uncharted territory, characterising the reliability of demand side provision and how you do that statistical problem.
I can't help feeling that thinking about storage as being there in some sense for extreme events and having to manage them is a bit of a red herring. I mean, if you have an extreme event, you use whatever you've got at your disposal.
Yeah.
And it doesn't really matter whether it's storage or you've got to pull on a really expensive oil plant, or you've got to declare that there's a system security issue and you're not prepared to export anything to France. You just use what you've got.
Yeah, I think where storage, I think yes, that's certainly true. But I think where storage may require some different analytical techniques. So, for instance, with most things to do with storage, you can only analyse them within a fully sequential model. For most purposes, it doesn't make sense to look at storage in a time collapse model. And also there may be some particular points where time or energy constraints on the storage mean that you have to you have to use a slightly different analysis picture.
Okay, I think probably if we sort of end general discussion now, there's several little groups I know that want to carry on individual conversations about one thing or another. So let's do that, and we'll resume tomorrow. Does anyone want to say anything about the program tomorrow?
We'll know when Robert Lees turns up.
Right. Okay. Right. Well, thank you, everyone.